Hey everyone. All right. So, the magnitude system is a different way of quantifying brightness. So far, so far in the semester, we've mostly been talking about brightness in terms of flux or luminosity. Magnitudes are a different way of doing that. That is, as you've seen, a little weird, a little backwards, but the numbers stay conveniently small. So it does have a nice, despite all of the historical baggage of the magnitude system, it does make the math a little easier sometimes. So how does this work? Let's see here. The main thing to remember about the magnitude system is that the lower the number, the brighter the star looks. Okay? In apparent magnitude, right? The apparent magnitude of a star is how bright it looks from Earth. So in other words, it's a way of talking about how bright the star appears, and that depends on flux. The absolute magnitude is how bright the star would look if it were 10 parsecs away, right? So not how bright it looks on Earth, because some stars are farther away, some stars are closer, but if the star were a fixed 10 parsecs away, then how bright would it look? All right, so in other words, absolute magnitude is a measure of luminosity, or it's another way of talking about luminosity, because if a star would look brighter from the same distance, it must be because it's a greater luminosity. If a star would look fainter from a fixed 10 parsecs, same as every other star, it must be because it's a lower luminosity. So, all right. So if you're talking about Akana or Bada, which one looks brighter as seen from Earth? Right? Which one appears brighter? Well, Akana is a magnitude 5, Bada is a magnitude 4. Which one looks brighter? Well, remember, the lower the number, the brighter the star looks. So a 4th magnitude is brighter than a 5th magnitude, so Bada looks brighter here on Earth. Which star is more luminous? Okay, well, if you want to know about luminosity, then you're looking at the absolute magnitude. All right, Akana is an absolute magnitude 4. Bada is an absolute magnitude 4. If they have the same absolute magnitude, then they must have the same luminosity. Which one is closer to Earth? All right. Well, remember that the definition of absolute magnitude is how bright the star would look. What would its apparent magnitude be if it were 10 parsecs away? So for Bada, right, Bada's absolute magnitude is 4th magnitude. In other words, if it were 10 parsecs away, it would look 4th magnitude. Well, in fact, it does look 4th magnitude. So how far away is it if it looks 4th magnitude and has an absolute magnitude of 4th magnitude? It must be 10 parsecs away, right? Bada must be 10 parsecs away because it does look as bright as it would look from 10 parsecs. So we know that Bada must be 10 parsecs away. Now what about Akana? Okay. Akana looks 5th magnitude. It looks fainter. If it were 10 parsecs away, if Akana were 10 parsecs away, it would look 4th magnitude. So if it were 10 parsecs away, it would look 4th magnitude, but actually it looks 5th magnitude. It looks fainter, right? If Akana looks fainter than it would look from 10 parsecs, then Akana must be more than 10 parsecs away. If it looks fainter, it must be further away from us than 10 parsecs. So which one is closer, 10 parsecs or more than 10 parsecs? Well, 10 parsecs is closer to us. All right, how about Ceriero and Darnin? Which one appears brighter? Well, Ceriero has an apparent magnitude of 0. Darnin has an apparent magnitude of 0. So they have the same flux, same apparent brightness on Earth. But which one is more luminous? Which one has the brighter absolute magnitude? Ceriero has an absolute magnitude of 2. Darnin has an absolute magnitude of 0. Which one's brighter? Well, remember, the magnitude system works where the lower the number, the brighter the star. Absolute magnitude works the same way as apparent magnitude. So 2 or 0, which one's brighter? 0 is brighter, right? 0 is lower than 2, so it must be brighter. So Darnin has the greater luminosity because it has the brighter absolute magnitude. Which one is closer to us? Well, again, you notice Darnin's absolute and apparent magnitudes are equal to each other. So if Darnin were 10 parsecs away, it would look 0th magnitude. Well, actually, it does look 0th magnitude. If it actually does look 0th magnitude, then Darnin must be exactly 10 parsecs away. All right. If Ceriero were 10 parsecs away, it would look 2nd magnitude. But actually, it looks brighter, right? If it looks brighter than it would look from 10 parsecs, then it must be closer to us than 10 parsecs. Right? If it appears brighter, it must be closer to us. So which one is closer to us? Less than 10 or 10? Less than 10 has a closer distance. All right. So if you want to know the exact distance, well, then we got to do that math on the next page, right? But at least given these numbers, unless the absolute and apparent magnitudes are equal, then okay, the distance is 10 parsecs. You can't quite just eyeball these two numbers and know exactly what the distance is, but you can at least eyeball these numbers and go, okay, if apparent magnitude is fainter than absolute, it must be farther away than 10 parsecs. If apparent magnitude is brighter than absolute, it must be closer to us than 10 parsecs. So at least you can get a sense of the distance, even if you can't get the actual value. If you want the actual distance in parsecs, then you need to solve this distance modulus equation. And right, little m is always the apparent magnitude, big M is always the absolute magnitude, d is always the distance in parsecs, and now we want to solve, if we know the apparent and the absolute magnitude, then we can solve for the distance. So, for Akana, apparent magnitude is 5, absolute magnitude is 4, so 5 minus 4 is 1. 1 divided by 5 is 0.2. All right, and then and then you got to find your anti-log or your 10 to the x button or whatever the button is on your calculator. What are we doing here, right? Remember that in order to solve for d, we need to get d out of the log function. How do we get out of the log function? Well, the general solution for any equation is that if you have an equation, a equals the log of b, right? If you have that a equals the log of b, and you want to solve for b, then the general solution is that b equals 10 to the a. So we just need to take, right, so if we have a equals the log of b, then b equals 10 to the a. So, in this case, a is little m minus big M over 5. So here's our a value, right? Then 10 to the 0.2 is, pull my spreadsheet up here, well, heck, we can program this to do the work for us, can't we? So let's just have little m here, that's 5. Big M here is 4. And then we'll say, all right, so step 1 is, parentheses, apparent magnitude minus absolute magnitude over 5. Okay. Step 2 is, take that value, take 10 to the power of that value, so equals 10 to the power of little m minus big M over 5 is, okay, 1.58. And then step 3 is, now what have we figured out, right? We figured out that b equals 10 to the a. What is our b? Our b is distance over 10. So we have that distance over 10 equals 10 to the 0.2 power. All right, and then step 3 is just multiply by 10, so that you multiply the 10, or you multiply both sides of the equation by 10, so that then d equals 10 times 10 to the 0.2 power. So the last step is take step 2 times 10. There's our distance in parsecs. That's just going to equal the answer from step 3. So that star, so Akana is 15.8 parsecs away. All right. So that was what? 1.58. And then 10 times 1.58 is 15.8. So Akana is 15.8 parsecs away. Right? You got to take 10 to the power of the magnitudes to pull the distance out of the log in order to solve for the distance in parsecs. All right. And then, so let's try the rest of them. All right. What about Bada, where the absolute magnitude is 4 and the apparent magnitude is 4 and the absolute magnitude is also 4? Well, if we say that the apparent magnitude is 4 and the absolute magnitude is 4, what did we just say a second ago, right? Absolute magnitude is how bright the star would look from 10 parsecs. Apparent magnitude is how bright it looks. So if it were 10 parsecs away, Bada would be 4th magnitude. But actually it is 4th magnitude. Therefore, it must be 10 parsecs away. Let's check our work here. There we go. Right? Then little m minus big M is 0. 10 to the 0th power is 1. 10 times 1 is 10. It's 10 parsecs away. Just what our intuition said it should be. Right? 4 minus 4 is 0. 10 to the 0 is 1. 10 times 1 is 10 parsecs. Bada is 10 parsecs away. Whenever the apparent and the absolute magnitudes are equal, you're going to subtract them and get 0, and then the answer is exactly the same. It must be 10 parsecs away. Okay, Ceriero. What did we say? What did we say about Ceriero? The apparent magnitude is brighter than it would look from 10 parsecs. So if the star looks brighter than it would look if it were 10 parsecs away, then it must be closer to us than 10 parsecs. How close? Well, again, like I said, hard to eyeball, but let's put our numbers into our spreadsheet and see what happens. Little m is 0, big M is 2. Little m is 0, big M is 2. 3.98 parsecs? Well, it's less than 10, just what we expected. So that answer makes sense. If you expected that the distance would be more than 10 parsecs and you got less than 10, or vice versa, if we expected that the distance was less than 10 parsecs, but we got a distance that was more than 10 parsecs, then we're getting an answer that we're not expecting, which means we need to check our work and see if we made a mistake or was our intuition just wrong. More often than not, it's just that you made a mistake in the math and need to check your work. So, but in this case, we got what we expected, 3.98 parsecs. So When the calculator gives you what you expect, it's probably because you did it right. And then what about darnin? Little m equals 0, big M equals 0. What happens when little m equals big M? 10 parsecs again, just like we expected. All right. So based on the above, what is the distance for any star whose apparent magnitude is equal to its absolute magnitude? Always 10 parsecs. Right. So that's why when the definition of absolute magnitude was made up, right? We said, all right, let's take distance out away as a variable, right? Let's say, what if every star were the same distance from us? Then how bright would it look? Because if every star is the same distance, then the only reason why a star would look brighter is if it had a higher luminosity. And so they said, well, what distance should we set all these stars to? And they picked 10 parsecs because 10 is a nice round number and it makes the math easy. So there you go. Any star whose little m equals big M must be 10 parsecs away. All right. I hope that makes some sense. Post your questions if you have them. And if this is making some sense, then on to the next assignment. Good job, everybody. See you then.